me. Actually, thanks a lot for inviting me, because this forced me to think about if our spin wave systems, which I want to talk about, are really suitable for neuromorphic logic or for anything which is a little bit more than Boolean logic. And so what I will talk about is, as a preface before I really start with my outline, is I will not show you that we have large neural networks made of spin waves, or that we have feedback loops or something like this. And I only can present you some first concepts for learning and how you could change the weighting in the neuron. What I will talk mainly about is how to shape these functions here, these transfer or activation functions, because we just want to build an all spin wave logic. So you have input spin waves and output spin waves, and they're processed in a spin wave device. And what we did so far is mainly linear wave superposition. So you can interpret, for example, these weighting factors as kind of encoded in the wave's phase, for example. But we all know that we need nonlinear functionality. And I want to show you principally how we are evolving from all linear superposition of waves to some nonlinear circuits. So since this should be a little bit like a tutorial, I want to talk a little bit about wave-based logic and spin waves in general. Then I will shortly show you the prototype of a linear spin wave logic element, the majority gate. Then I show you another linear application, which is the frequency multiplexer and spectrum analyzer, which is based on a particular feature of dipolar dominated spin waves, which are acoustic beams. And then we go more towards neuromorphic computing, so towards integrated magnonic circuits. So I will show you a concept for a magnonic half adder, which is quasi-binary, but which is also already using nonlinear functionality. And then in the end, I will shortly show you how we would like to evolve into something like a magnonic neuron, which is somehow realized in terms of an analog magnon adder. So what is wave-based computing? So what we have is usual CMOS computing schemes where you have a scalar variable, which is simply the presence of an electrical charge. The transport is really driven by potential gradient, so by a voltage, and the logic is mostly based on CMOS-based transistors. In the wave logic, everything is a little bit different, because we change to a vector variable, which has amplitude, phase, frequency, and wavelength. Our transport of information is not given by a potential gradient anymore, but by wave propagation. So you have completely different possibilities to engineer energy and information transport. So this leads to a completely different circuit design. And what we usually use in logic, at least in the linear stuff, is interference phenomena. So because with these interference phenomena, you can quite easily realize special logic functionalities like this majority gate. So just shortly, what are spin waves and magnons? I don't think I have to go too deep inside, because it has been mentioned sometimes. So if you have the Landau-Lifshitz equation, and you look for a solution which is spatially dependent, so beyond the ferromagnetic resonance, you find that there are solutions which are the spin waves. So the spins do not precess in phase, but they have a spatial dependence where you can assign a wave vector to it. So that's it. Principally, it's quite similar to other quasi-particles like phonons or also plasmons. And on the other hand, we have the duality of the particle and the wave. So in the quasi-particle, we call the magnon. You can assign some energy, quasi-momentum, and spin. And the nice thing is, in special materials, this can reach up to 500 nanosecond lifetime. So it's a quite long lifetime if you think about data processing, if you think about clock speeds of gigahertz. This is more than enough. So how we describe the spin waves usually, so you have to analyze principally the effective field in the Landau-Lifshitz equation, and you have different contributions. So what we usually consider is dipolar interaction, which is usually described by a Green's function, and that in the spin wave dispersion, this leads to a geometry dependent and really complex contribution. If you have symmetric exchange, or Heisenberg exchange also called, you get usually some kind of parabolic dispersion, and with anti-symmetric exchange, so DMI, you can end up in some linear dispersions which are completely non-reciprocal. So just to compare what is so nice about magnons in comparison to electromagnetic waves, it's simply the scale. So here I've drawn you principally the same frequency scales for photon and for magnon. And here you see the wave number, and you see the wave number is 10 to the 3 to 10 to the 5 times higher. So that simply means our wavelengths are much, much smaller at the same frequency. So you can build a gigahertz device which with microwave is in centimeter range, is with spin waves in below micron range. And another thing is these waves travel quite slowly. So principally we have a time-resolved investigation which is possible, but this is usually more interesting if you think about experiments, but it's also interesting if you talk about data processing. So if you want to have a delay of your electromagnetic signal, there is a way principally to transform it into a magnon which is traveling really slow, and then in the end transform it back to an electromagnetic wave. So why should we use spin waves in comparison to other waves? So I already said a little bit about electromagnetic waves, but let me give you some features about spin waves in addition. So you can principally go up to terahertz in wavelengths down to nanometers. So this is here the measurement of inelastic tunneling spectroscopy. If this is feasible in technology, I don't want to talk about it, but principally these waves can be extremely short and extremely high frequency. You have efficient nonlinear effects, there I will talk later about. You can design the system completely non-reciprocal. So you can, with DMI and dipolar interaction, multilayers, you can design a system where information can only flow in one direction and not back. So principally you have a lot of freedom to design all these band structures. We are working always at room temperature, and we have a quite good CMOS compatibility via the spin Hall effect, for example, or spin orbit torques. We can directly connect to conventional electronics. And you can use magnetic principally states to channel spin waves, like here in these two main walls, so you can create spin wave channels which are smaller than the structures you can pattern with E-beam or something like this. So there are quite some examples of spin wave logic. So here the majority gate I will talk about in a minute. Then we have something like the magnon transistor, where you principally use nonlinear magnonic interaction to control one magnon flow, which is strong by a weak other magnon flow, by simply enhancing everything in the magnonic crystal. Then from the US, there are some more fancy approaches, I would say, which is like holographic memory or factorization problems using spin waves. This is still, you see, it's all in the millimeter scale, so this is a little bit far away from real technology. But there are also people from Intel, or now also from IMEC, and here the engineers, you already heard a talk on Monday, that they also trying to move in this direction. They are more focusing really on the technologies. They are thinking about how to connect everything with CMOS. So there are now also first benchmarks from companies and engineering groups where they have a look if these circuits could outperform CMOS, for example, at any point. And the result is they could only be better if you go to ultra low power applications, like you would need it for mobile devices or the Internet of Things. So we will not be super fast, but we could be maybe extremely energy efficient. That stays to prove, I would say. So now let's have a look on this spin wave majority gate. Principally, it works in exactly the same manner than Wolfgang Porrett presented on Monday. You have here your three inputs, and your output should be the majority of the inputs. And with wave, this is quite really easy. You encode the 0 in phase 0 and the 1 in phase pi, and then you just let them interfere. And then the phase of the output wave has simply the phase of the majority of the input waves. So this is a really linear, easy superposition. And as it has been pointed out on Monday, principally with this gate, you can replace a lot of other gates. So we have created a macroscopic prototype first, where you see here principally all the inputs. We excite the spin waves using some quite large antennas here by applying microwaves to the system, and then we combine them in this trident structure and read out here via a real-time fast oscilloscope. And what you see is exactly what you, it's a little bit strange here, expect. So principally, this is really the output from the oscilloscope, and you see here are the different combinations of the input waves, and depending on if the majority has a phase 0 or a phase pi, you get out a wave which has the correct phase. So principally that works, but you already see a big problem in this wave logic, that the amplitudes are different. So if you now do a readout of your system, everything is fine. But if you want to interchain many majority gates, this will not work, because the amplitude needs to be renormalized. So principally that also tells you that you need a lot of nonlinearity to make really a large logic circuit working. So at the moment we are working to do that really nano, but it will work in the same way, so there is no big difference. And I should say that IMEC also has already fabricated a much easier design of this device on the micron scale. So this is something really where industries now, or industry close people are looking on. Now let's go to something which is a little bit more specific for spin waves, especially for dipolar spin wave. This is this frequency multiplexing and using acoustic beams. So frequency multiplexing is quite easy. So you have different signals which are encoded at different frequencies, and with a multiplexer you merge them into the same physical channel, and then you transport it or you manipulate it, and in the end you demultiplex it and read out the different signals. So this is all about optical data transmission principally. And how does it look for spin waves? So here you see our waveguide. We see an antenna which is exciting the wave, which is launching it. It runs here. So, and with our Boolean light scattering, we can principally measure the spin wave intensity and frequency. So what we did here, we first apply something at 11 gigahertz, then we have something at 14 gigahertz, and then here we have a simultaneous propagation of the two signals. And to the best of our resolution for these really low powers we use in this experiment, they don't interfere at all. So principally you have a simultaneous transport of or at two different frequencies. But the big problem, what is, how do you multiplex and demultiplex the signals? So in the majority gate, this, for example, if you would be able to do it, you just would increase it by a factor of 2, so the power. So this has to be scaled somehow. But I guess the idea why we want to do this is quite obvious. So what we now use are acoustic-like spin wave beams. So what is acoustic? Principally, when you inject a spin wave into a large pad from a small waveguide, what you see here in this experiment is you form really nice beams, which are extremely well focused. And the creation of these beams and their propagation angle can be understood from the spin wave dispersion relation, because it's completely anisotropic. If you propagate along the magnetization here, you have almost no group velocity, so almost no dispersion, whereas you go perpendicular to the magnetization, you have a completely different dispersion relation. So how does this now lead to acoustics? So if you look on the isofrequency curve, so all the wave vectors which have the same frequency, so for an isotropic system, this would be just a circle around 0. And in this case, the circle is transformed to a line here. And now if you think a little bit about dispersive media, you know that the group velocity is always perpendicular to these isofrequency curves. So what happens here is the energy of this particular k vector will flow in this direction. But if you look on the k vector, or on the group velocities of the other k vectors, they point in the same direction. So actually, there are many different waves here in this area, but they all transport energy in the same direction, no matter where the phase is going to. So, and if you now calculate this angle as a function, for example, of the parallel k vector, you find that you get some slight variation, but in the end, you just have a small change in the angle. So there's some degrees when you change the k vector for quite broad range. So if you now do a model, what k vectors are excited by your source, so principally by the input into the pad, you can project this on this curve, and you see you will get a beam in this direction, so under 78 degrees, let's say. And if you do this now for a different frequency, you will end up with a different angle. And this is the way we principally can steer information in our unstructured systems simply by changing the frequency. So if you would have, for example, a tunable STNO which would change frequency by changing the current, it would also emit in different directions, which could be quite interesting if you want to have a reconfigurable network. So we did some micromagnetic simulation principally to verify if this is feasible with our material parameters. And in the simulation, it works quite nicely. So at 9.5 gigahertz, we can channel to one output, and at 12.5 gigahertz, we simply channel to the other output, and all what is behind is simply the anisotropic dispersion. There is no grating or anything like this, which is doing a diffraction. So now we also try to realize it, and I was surprised that it works so well. So we use this microfocus spiral light scattering, so principally the inelastic scattering of a photon with a magnon, and we analyze principally the frequency shift and the intensity of these scattered photons to get an idea about the intensity of these magnons. And this with a spatial resolution of about 300 nanometer via some microscopes. So principally really scan the microstructures. And so what you see here is the sample has been fabricated by IMEC. So it's CoFab 30 nanometers thick. Here you have the microstrip antenna, which is launching the spin wave into this pad. And here we have two outputs, and you see they are asymmetrically placed. So you would assume that the channeling will be different and will be frequency dependent. And principally, that's exactly what we see. So if you go with the microscope here, scan the frequency, you see there is a really particular frequency which is channeled into this output. And if you go to the other output, which is at a different angle, you nicely see that you get a completely different frequency which is channeled in this direction. So now you might ask, why is this peak much wider than this one? And the answer is quite simple. If you look on the beam angle versus frequency, you see here the curve is much steeper than here, because at really high frequency, everything gets more and more isotropic. So there you start to lose this caustic behavior. That's why we have a different width of these beams. And you can also, just for clarity, image the whole structure, and then you nicely see principally at one frequency you channel everything into this left output, and at the other frequency you channel into the right output. So I guess this is really the first experimental realization of this spin wave frequency demultiplexing. And okay, the multiplexer would be just if you excite here on this side, and everything should be in this case reciprocal and should propagate then to this output. Actually, what is also quite interesting in this case, because we have been talking about spectrum analysis on Monday, is simply you could take these two signals and get the ratio of them, and then this ratio of the two signals directly tells you in a certain range which frequency has been applied to your device. So principally, if you would have a way to have a really efficient readout of the intensities, you could build some microscale spectrum analyzer with some quite bad resolution, but it would be a quite small device compared to the large devices which are used at the moment. Okay, so now I will leave the area of linear spin waves, and I will go more towards integrated magnetic circuits, which in the end should use nonlinear effects. So the first thing is what we wanted to build is a little bit more advanced circuit, which was this magnetic half adder. And why do we want to go to this integrated circuit, so to this all magnetic circuits? So many people pointed out by now that the energy consumption in all our experiments is not in the spin system. There, the energies are really, really low. So yeah, at the nanowatt scale usually. But what we apply is always much larger because simply the coupling to the spin system is really, really small. So the amount of the microwave which is simply absorbed by my magnetic material is ridiculously small. Most of the microwave is simply reflected or transmitted and nothing is absorbed. So this is actually, I guess, one of the biggest problems when you talk about using spin waves for anything, that the coupling to the system is really low. So one way to make this a little bit less disadvantageous is simply you have one input at the beginning of your circuit and one output at the end of your circuit, and in between you do some quite complex calculation, but it's all in the spin wave domain. And then you pay this penalty only twice principally, instead of having always an interconnect to CMOS going back to the spin system and back and forth. This will never be super efficient. And on the other hand, we are also working on how to improve this conversion efficiency. But since this is really unexplored physics, no one really can predict to which degree this will really improve. So if we will ever get here to an efficiency which is better than 2 orders of magnitude or something like this. So the system we have chosen is this half adder. So for those who do not know how this works, principally you have two inputs, A and B, and then you have a truth table which defines you some sum, so which is the first binary principally, and some carry, which is simply the binary for the next higher 2 to the power of n plus 1. So if you combine many half adders, you get principally a full adder for many bits. At least that's how I understand it. I'm also not an expert in data processing, I have to say. So the usual realization is like this. You have the two input signals, you split them, you cross the interconnects, and then you have the XOR gate and the AND gate, and then you have principally the easiest realization also in CMOS, but it's definitely not the most efficient. So there are other ways to build this which are more efficient, but this was principally our inspiration. And what we found was simply, okay, we need a crossed interconnect. And that's not so trivial, because how you do it in spin waves, principally. And so how do you do in electronics? In electronics, it's actually interesting. You always need to go 3D, principally. So you always have an insulating layer in between if you connect 2 and 3 and 1 and 4. And that ends up in quite complex structures. And there has been a lot of work has been devoted to also, as far as I understand, in these companies, how to make this more efficient and how to use novel materials for this. But it's always quite complex and extensively 3D. With waves, principally, you could go to 2D by simply using coupling phenomena. So this is simply taken from optics, this idea. So principally, if you have a wave, the wave can couple from one waveguide to the other without principally, if it's still linear, without interacting with the other wave, which is going from here to there. So, and this has already been shown in macroscopic samples by these Russian groups. So principally what you have is you inject the wave here, it couples to the other waveguide, couples back, force, back, force. So if you do the right trick and couple it out, as long as it's there, then you have realized this directional coupler. So we had a look on this, how to make it really small and if it would still work, what would be the efficiency. So we did micromagnetic simulations. We looked on 2 coupled waveguides made of yttrium iron garnet. And we always use in the further simulation, which I show you, we always use really the parameters from materials we have in the lab. So I try not to invent the material which is not existing, I have to say. But it's quite hard in the end to fabricate it still. So, and what you see then in the micromagnetic simulation, you excite the wave here, it couples to the next waveguide, so you transfer energy, you transfer it back and forth and back and forth. So principally that's simple scheme of coupled oscillators. You transfer energy between the 2 strings. There is no big physics which are really behind it. So how do the spin wave dispersion relations look in this case? So what we have is we have the waveguides which are magnetized along the long axis. So you have a little bit of a wave which is called backward volume wave, which has a slightly negative dispersion here. But since the system is so small, this effect is almost negligible. So if you would go to quite large structures, you would really see that there is a large dip here, where there's a large region where you have a negative group velocity. But in our case, it looks more like a pure exchange wave, actually. And then if you go from this single waveguide system to a coupled waveguide system, and as in any coupled system, you get a splitting of the modes. So you get a symmetric mode and the asymmetric mode. And here, principally, you see the 2 mode profiles. So in the symmetric case here, it's oscillating principally in phase. And in the antisymmetric case, it's oscillating out of phase. And principally, you see there is always at a given frequency, there is some delta k, so some difference in wave number. And this coupling length, which simply means how long does it take in space to couple from one waveguide to the other, is simply given by this inverted principally difference of the wave vectors. So with this physics behind, you just can engineer your system, and principally the only engineering task here is to avoid reflections. So what you want is that the wave is going here and coupling and coupled to the next waveguide without having too many reflections. And that's actually not so straightforward, because also spin waves have impedance, and depending on the mode structure, you can have a lot of reflections and backflow in your system. So that's why, for example, we introduced this small shift in the 2 coupled systems. That's simply a trick to avoid too much reflection. And if you now analyze the output of these structures, you see that as a function of wave number, the amount of spin waves which are ending up here from this input is oscillating. And that's simply because the wave number influences the coupling length. So we shift principally from cases where we couple to the other waveguide to cases where we stay in this direction. So we can pick principally these 3 frequencies to illustrate this. For one frequency, we completely or almost completely channel the wave to the other waveguide. So in this case, we really have the crossing, which we would need for the half adder or for any larger circuit. And for the other cases, so if you choose a different frequency, it's simply a splitter of power. And for even higher frequencies, you see you couple to the other waveguide and then you couple back. So principally for this frequency, it behaves like a simple waveguide which is uncoupled to the other system. This is all principally based on principles of photonics. So there's nothing new, but okay, we have different degrees of freedom that you usually don't have in photonics. So principally, you can engineer the coupling strengths by the magnetic ground state. And the interesting thing is, so if they are both parallel, the coupling is weaker than if they are antiparallel, simply because the out-of-plane component of the dipolar interaction changes sign if you start to oscillate into the other direction. So principally what you find is the coupling lengths in the antiparallel state are always lower than in the parallel state. So principally I can reconfigure my device in this case. So for example, for this waveguide, if I'm in the parallel state, it's simply a simple waveguide. If I go to the anti-parallel state, I end up in a directional coupler, which is crossing the energy to the other waveguide. So principally, this would be an idea how you can reconfigure a magnonic network purely in the spintronic domain. The nice thing is that also works if you have domain walls, at least in these simulations, because everything is super small, so there are almost no reflections from the domain walls. And you see, in this case, it's similar to the antiparallel alignment, because locally the spins are always antiparallel aligned. So you get a similar transmission here, but you could simply play a trick and say, okay, what will happen if I put the domain wall only in one of these directional couplers? So principally, I could imagine that I have some kind of racetrack memory here with one domain wall, which I will shift back and forth. And the other waveguide is simply without any domain wall. So I have an area where I have parallel states. So there is a weak coupling, and an area where there is an anti-parallel alignment, so strong coupling. So if I shift the domain wall back and forth, I will also tune my transmission. So in this case, you could think about, you create some reconfigurable magnonic synapse, because you can simply change the transmission and then wait for the next operation and readjust it again until your network has somehow converged with a good solution. So now we have this directional coupler. Principally, we insert it in our system as the crossed interconnect. So you need to design principally the coupling in a way that the frequency you use is exactly corresponding to this case. So it's not a multi-frequency approach anymore, I have to say. So now let's have a look on the AND gate. And truth table of AND gate probably everyone knows. So the most stupid approaches would be principally try it with linear encoding. So you try to encode in amplitude, it does not work. You try to encode it in phase, then it's even worse, because sometimes you have no wave output. So that's an undefined state. So principally you can easily come up with a conclusion that there is at least no simple linear realization of wave-based AND gate, which can be easily implemented in a magnonic network. So what you could think is, if you look on this, if you could do a nonlinear transformation which would make these two vanish to zero, then it would be an AND gate. So what you need is nonlinear signal transformation by a nonlinear transmission of a device. And to principally increase the nonlinearity at really low energy densities, which in your input, you usually use a cavity. So we were thinking about why not using a magnonic cavity principally to enhance a little bit these nonlinear effects. And the nice thing is it's all there in optics. So I just saw this morning that there was a new Nature paper about creating frequency comps and lasers using exactly this kind of structures. So what you have is you have a waveguide and it's coupled to a ring, and part of the wave is coupled to the ring, it's running once and partially coupled back. So you can describe this analytically with the well-known theories from optics. And then if you hit the resonance condition, so principally that the phase accumulation is just 2 pi times a natural number, then you can end up in a case where the critical coupling condition is fulfilled, which simply means is that the dissipation in your ring is matched to the coupling. And in this case, you will have completely destructive interference in the output. And that's what is shown here. So principally here, the frequency, with the frequency, we tune principally the coupling and this phase accumulation. And you see at the resonances, you see a strong drop of the transmission. And in this case, everything is reflected or absorbed in this cavity. So this is obviously a quite interesting approach, and especially because you can go nonlinear with this device. So here's principally the micromagnetic simulation to this analytical model. Fits quite well. So here you see what happens if you have a really low spin wave amplitude. At the given frequency, you have this resonant condition which is fulfilled, and the transmission drops strongly down. So now if I increase my excitation field, so principally my input spin wave, I will have a nonlinear shift. And that simply leads to a change of the dispersion relation. In this case, the shift is negative, so principally the whole dispersion relation is going down. So for a fixed frequency, you will have a higher k vector, and that will completely change your resonance condition. So what will simply happen is that in this case, this minimum will move to a different frequency. Actually, it doesn't, for our purposes, it would not matter if it would move into the other direction. It would just, what we just need is that this resonance condition is changed, principally, because of the nonlinear shift of the wave vector. So what you can now think about, we are always working at a fixed frequency in our experiments. So if we now will stay here at this resonance condition for low input powers and increase the input power, what you see is the transmission will go up, significantly go up. So you put more energy in the system and you get much more energy out of it, because you simply increase the transmission drastically. So you can evaluate this. So in our experiment principally, or numerical experiment I would say, this micromagnetic modeling, you have in resonance, you have 3.1% of transmission, and if you increase simply the spin wave amplitude only by a factor of 2, the transmission goes up to more than 20%. And that's exactly some kind of nonlinear function which you actually use for also in neuromorphics, that principally we can, with these cavities, we can design these functions quite, I would not say arbitrarily, but you could think about any other shape and think about how to realize principally this transfer function. So with this, we can simply build this half adder, or at least in simulations. So it looks a little bit complex, but it's actually not too complicated. So we have two splitters. We have our coupler, which is simply the cross connect. Then we engineer these distances here to have a destructive interference of the two inputs here and a constructive interference in this point. And then we add here this nonlinear cavity, which has been inspired by integrated optics. So let's have a look on the operation. And okay, this is somehow in agreement. What we choose is the length here, what we can fabricate in the lab. So I guess the width here is 100 nanometers. At the moment, we see spin wave propagation in around 50 nanometer wide waveguides. So it should be feasible to do this design within 1 or 2 years, I would say. So here is principally the simulation. So we have no input here, one input here. So what you see is part of the spin waves is channeled along this direction and ends up in the sum. So we have some signal here. And all the spin waves which are going in this direction, they are simply absorbed in the nano cavity because it's in the resonant coupling condition. So now what really changes when we increase or when we switch on both inputs is simply that now we have here some destructive interference, so all energy principally is reflected here, so the sum goes to 0, and here they interfere constructively, and because of the nonlinear shift, the cavity is principally opened. So we have a strong flow of energy now through this device, so principally we just changed 1, 0, and 0, 1. And this is a little bit more in numbers, so principally you see here, the carry is really low if we have only one input on. And here we have still some residual signal in the sum, which should be, strictly speaking, exactly 0. But okay, you could think about some thresholding processes to avoid this also. And in this case, we have really a strong signal and the carry. So this is somehow first proof of concept study, how you can build and integrate all Magnon circuit. The computation here is quite slow, so it takes some hundreds of nanoseconds for the whole system to reach an equilibrium, because we designed it in a way that it's really large that we can easily map it with BLS. Nevertheless, the whole computation only takes about 1.5 attojoule in the spin system. So if you would be able to completely transfer the RF energy, so the microwave, into the spin system, this would be a fantastic device. But we all know that this is not possible at the moment. The fundamental problem in this device principally is that this configuration and this configuration has almost the same output energy, but it has a phase shift. Simply like in this design here. So at the moment we don't encode any logic here in phase. The encoding is completely in amplitude. But if you want to do now a chain of half adders, this will not work anymore, because they should be logically equivalent, but they are not in phase. So any interference experiment which will be performed later will show a completely different behavior. So there's no network possible here. So we thought a little bit, and then we said, okay, we should not stick too much to this CMOS-inspired system. And our student came up with something which looks even much more simple. So it's simply the combination of two directional couplers. One is going in the linear regime, one is going in the nonlinear regime. And so I will shortly explain what this means here afterwards. But the good thing is here, the amplitudes and phases are matched. So principally this design you could build into a chain of different half adders to create, for example, a full adder. So this directional coupler is exactly like I showed you before, so there's nothing new. It's just used as a power splitter and not as a completely coupling system. But the nonlinear directional coupler is quite interesting. So what we have chosen here is a system which has a really strong coupling. So the gap here is only 10 nanometers. And that leads to quite interesting mode picture, especially this antisymmetric mode here is super flat. So you see here, a small change in the frequency will lead to a large change in the wave vector. And that's exactly what you need to have a really strong nonlinearity, because the nonlinear shift will be in frequency domain principally. And if I shift my frequency, my resonance frequency here about some 100 megahertz, I will really change my K vector completely. So all phase-based mechanisms will be completely changed, like the coupling, for example. So principally, you can calculate here the output of this device. So this is again the coupling to one of these output as a function of frequency in the linear case. And then you can go also to the nonlinear case. And I have to say, there's extensive theory about nonlinear magnonics. And this is simply the simplest approach you can do is you just add some nonlinear coefficient, which is so nonlinear frequency shift, which is proportional to some interaction element between the magnons and the magnon intensity. And okay, then principally there's the whole theory where you really analytically can calculate this. So it's just to show you that there exists a lot of ways to describe analytically also nonlinear magnonics. It's not that we are restricted to some linear cases. And with this, principally, you can also model a nonlinear excitation. In this case, you just double the amplitude of the incoming wave, and you see that the coupling is slightly shifted, and especially in this region where it's so flat here, the band, this leads to a large change. So we will work here at this particular frequency, and you see between the red and the black curve, so between 2 millitesla excitation and 4 millitesla excitation, you get almost a complete shift of the power. So principally in the linear case, you transmit everything, and in the nonlinear case, which is just twice the amplitude, you completely suppress any channeling. So here you see principally that's why we call it the linear directional coupler. The first one and the nonlinear directional coupler. The linear one is principally independent of the input spin wave amplitude, whereas the nonlinear one is really strongly dependent. And principally with this, you can really see that this working principle works, so that the device actually works. It works exactly, you see, in the same way that we saw it before, but now we really have something which we could chain to get an even more complex network. And with this, I want to leave a little bit the things we did, which have been inspired by Boolean logic, obviously, and want to go to some analog Magnon adder, which we have in mind to develop further into a magnonic neuron. So principally, what is the concept of this Magnon adder? We have a resonator, we have an input, which could be the neuron or the synapses which come to your neuron. So you have an input. In this case, this is just a waveguide, and this waveguide is dipolarly coupled to this small piece of waveguide, which is our resonator, and then we have some output. And the interesting thing is here, we have inside the resonator, we have some pumping area where we pump energy into the system. And in our case, we use parallel parametric amplification. And the idea is simply, we use a resonator where the natural spin wave damping is compensated. So we have an infinite lifetime of our spin waves in this device. And then we add up simply spin wave pulses, which arrive at with a special delay time. So you see here, principally, you have 4 input pulses. They have different amplitudes, and the resonator will simply sum them up. And in the end, you will get in the output simply the state which corresponds to the sum of all input pulses which have arrived before in time. So this is obviously not a neuron because it's still completely not linear, but what we then want to do principally, you can add a nonlinear magnonic element to give a threshold functionality, and then principally you can create some device which looks like a firing neuron. So if you reach some certain threshold, the cavity here will open up and will eject a magnonic pulse. So maybe just some words about this parametric amplification, because this is something we did really a lot, and also in microstructures. So here's a review also. So what you do is you have a pumping field which is in frequency twice as high as a spin wave mode that you want to amplify. And this field is parallel to the static field. So principally it only acts on dynamic components of the magnetization, not on the static one. And the requirement for this to work is you need some elliptical trajectory, which you usually have in thin film systems simply because of the shape anisotropy. And the quasi-particle picture, simply this means one microwave photon splits into a signal and an idler magnon, which have some certain phase relation. So principally here you see the photon frequency, and then you split into magnons. What you can do now, principally, this is some older experiment. You inject the spin wave, you let it propagate, then here you have your parametric amplifier, and what you see is principally if you have only pumping, almost nothing happens. Here you have only the excitation of the spin wave. Then you can have the case where the phase is, let's say, not well chosen. So the phase between the amplifier and the incoming spin wave. So also here almost nothing happens, especially there is no amplification of the spin wave which is traveling away from your antenna. But if the phase here, the green line, if the phase is properly chosen, you see inside the amplifier you get a strong amplification and you can reach a much longer distance principally with your spin waves. And since this whole phenomena is completely depending on the phase between the two waves, it's actually also a quite interesting way to continuously transform the phase of the spin wave to a spin wave intensity. Because, for example, if you measure spin wave intensity via things like spin Hall effects, what you get out is a DC voltage which does not depend on, which does not tell you anything about the phase of your wave. So if you are able to convert the phase of your wave into intensity, you could use these methods also to read out using phase-sensitive elements like the majority. So this is principally the way we want to realize this amplification. So now back to this Magnon adder. So this amplification obviously has a dependence on the pumping field. And here now, what you see here is the gain factor inside this resonator as function of the pumping field. So principally the gain factor tells you a little bit how stationary your system is. So if it's 0, then amplitude which is entering the resonator is kept forever at the same intensity. If it's below 0, you exponentially lose the memory of that pulse with time. And okay, if it's above 0, then you amplify the system and in the end you will get to some nonlinear state or chaotic state. That's something we did not explore yet, I have to say. So with this, you principally can say, if I really want to simply add pulses, I just should work at G equals 0, because then there is no change after some transitional regime in my spin wave amplitude anymore, and I just add up all the pulses which are coming. And we tried this. So here's an example from the simulation. So there are different ways to sum up to 10. For example, you can inject 10 directly. This is the black line. So you see there's some, this is principally the energy in your resonator in this mode which you pump. And you see there with the number of pulses, so with time, this has some transitional dynamics and then reaches some steady state equilibrium, which we define then as 10. And you see now, this simply means we inject 5 times the amplitude of 2, and here 10 times the amplitude of 1, and here we subtract from 20, 3, 3, and 4, and you see that all these different combinations, after some time, they reach the same value. Principally, the subtraction is quite easy, so we just do a phase shift of 180 degrees of your incoming spin wave, then you can also subtract. So you reach a common value, and this is linear over a really large range. So in the way we have chosen the excitation amplitude principle, you can count up roughly up to 1,000. So we can directly get from the energy in our resonator, we can directly see how many pulses have been accumulated. And it does not really matter when they came or what was the, you really just look on the total sum of the device. So obviously what I learned, I guess I'm not sure if I got that right, it would maybe better to operate this device in this regime where you don't have an infinite memory of everything what has been before. But okay, that's something we can easily realize, so we just use a little bit lower field and then we have different correlations. And you can also think about using here simply functionalities like, first, for the first pulses, you use something which is below 0, just to give you some finite lifetime of your memory, and then you use a really strong pulse to amplify your signal in the end and reach a special output limit where you can then reach your nonlinear functionalities. So I think there are many ways which we can work with. So I hope we will be able to realize this in the future in our GIG nanostructures. And with this, I would like to acknowledge all the people who contributed, so the Kaiserslautern team, my boss, Burkhard Hilbrands, and André Schumack, my colleague, Thomas Brecher, who is principally the expert for all this parametric amplification, and the students which actually do the work, so which create the structures and do the simulations. Thanks also to all the IMEC team, in particular to these people who contributed to this acoustic sample. And for theory support, I would like to thank Roman Werber from Ukraine for principally modeling our systems with some Hamiltonian theories. So thank you for your attention.